A multiplexer is basically a circuit which has many inputs, and it will select one of the inputs and connect it to the output depending on the inputs applied at the select lines. So inputs will be written as I0, I1, I2 to IN, while the select lines will be I0, I1 to IM, and this will be output Y. So total there are n number of inputs. So sorry, this will be n minus 1. So there will be n number of inputs, and this will be m minus 1, and there will be m number of these lines which are called control inputs or select lines. The relation between control input and inputs or select lines and inputs is 2 raised to power m is equal to n. This relation should be always satisfied in case of multiplexers. A multiplexer has many inputs and single output. Depending on these input at the select lines, it selects one of the input and it connects it to output. So a multiplexer is basically a data selector which select one of the lines at the input and connect it to the output. Now we'll see first 2 is to 1 multiplexer. A 2 is to 1 multiplexer will have two input. Uh, one will be I0, other will be I1, and there will be one select line S0. This is 2 is to 1 multiplexer, and one output Y. Now this multiplexer, depending on the input at the select line, it will connect one of the inputs to the output. So S0, depending on the value of S0, Y will be decided. If S is 0, then I0 will be connected to Y, then Y will be I0. If S equal to 1, then I1 will be connected to output Y, so output Y will be I1. So depending on S0, there will be different output Y. Now for this multiplexer, we will write its output equation. Output equation Y can be written as Y equal to this I0 into 0 plus I1 into 1. This will be equal to, sorry. Now output Y will be written as, this is 0 will be written as S0 bar into I0 plus S0 into I1. This will be the output of this multiplexer, 2 is to 1 multiplexer. Now we'll see implementation of this 2 is to 1 multiplexer. This is the expression for output. S0 will be select line and will have its complement also. There will be two inputs I0 and I1. Output Y will be S0 bar into I0, S0 bar into I0, and S0 into I1. This will be passed through an OR gate. This will be final output Y equal to S0 bar into I0 plus S0 into I1. This will be the final output of this multiplexer. The symbol for multiplexer will use this, but rarely it is seen in the examination or any book. These are the inputs and these are the select lines, and this is output. Now we'll see 4:1 multiplexer. Multiplexer is also abbreviated as MUX, MUX, multiplexer. A 4:1 multiplexer will have 4 inputs: I0, I1, I2 and I3. There will be 2 select lines, S1, S0, and one single output Y. Depending on the inputs at this select line, one of the input will be connected to Y output. S1, S0, there will be 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. The output Y will be dependent on the inputs given to S1, S0. If S1, S0 is 0, 0, then Y will be I0. 0, 1, Y will be I1. 1, 0, Y will be I2, and for 1, 1, Y will be I3. So for expression for Y can be written as S1 bar S0 bar into I0 plus S1 bar S0 into I1 plus S1 into S0 bar into I2 plus S1 S0 into I3. This is the final expression for 4:1 multiplexer, and it can be implemented. Now we'll see one question. Implement a 4:1 multiplexer using 2:1 multiplexer. Now the implementation can be done easily. First, we know that a 4:1 multiplexer has 4 inputs: I0, I1, I2 and I3, and there will be one output. There will be 2 select line, S1, S0. So if we implement this circuit using 2:1 multiplexer, we'll make sure that it should have 4 inputs and 2 select lines. This is a 2:1 multiplexer. This will have 2 inputs. We will give first 2 inputs to this 2:1 multiplexer. Again, we should have 2 more inputs, so we will have to use one more 2:1 multiplexer. This multiplexer will have these 2 inputs, I2 and I3. Now both the outputs will be again given to a 2:1 multiplexer, and it will generate an output Y. Now we will have to connect the select lines. Select lines should be connected in such a way that the lower levels should be given lower bits of the select lines. This is lower level, this is lower level, and this is higher level. So here the select line will be S0. Here the select line will be S0. In one level, select lines to all the multiplexer should be same. and the remaining select line S1 will be connected here. Now we will verify the truth table of 4 is to 1 multiplexer. S1, S0, 0, 0, 0, 1, 1, 0, 1, 1. These are the S values, and Y will be I0, I1, I2 and I3. Now we know that if S1, S0 are 1, 0, then output should be equal to Y2. So put S0 equal to 0, 0. If S equal to 0, then the upper input will be passed. Upper input will be passed. Now if S equal to 1 for next multiplexer in the next level, S1 equal to 1, then the lower input will be passed. So output Y will be equal to I2. So it is working. Now I'll say 8 is to 1 multiplexer. 8 is to 1 multiplexer will have total 8 inputs, I0 to I7, while there will be 3 select line S2, S1, S0 and 1 output Y. This is 8 is to 1 multiplexer. S2, S1, S0, 0, 0, 0, 0, 0, 1. 3 select lines means there will be 8 combinations. This will be the 8 is to 1 multiplexer. Now we will implement 8 is to 1 multiplexer using 4 is to 1 or 2 first 2 is to 1 multiplexer. 8 is to 1 multiplexer will have 8 inputs and 3 select lines. So our circuit should have 8 inputs. So we'll require 4 2 is to 1 multiplexer which will have total 8 inputs. This will be I0, I1, I2, I3, I4, I5, I6, I7. Now the output of these two multiplexers will be given to the another 2 is to 1 multiplexer in next level, and finally the output of these two multiplexers will be given to another multiplexer. It will generate output Y. Now we'll connect now select lines. Select lines will be 3 S2, S1, S0. We know that the lower levels will have lower bits of the select line, means S0 will be here, S0 will be here, S0 will be here and S0 will be here. In the next level select lines will be S1 and in the last level select lines will be S2. So this is the implementation of 8 is to 1 multiplexer using 2 is to 1 multiplexer. So uh, we first implemented a 4 is to 1 multiplexer using 2 is to 1 multiplexer. So 4 divided by 2 will be equal to 2. This 2 will be taken here. Now this 2 will be again divided by this 2 will be equal to 1 plus 1. Total required multiplexers were 3. Then we implemented 8:1 multiplexer using 2:1 multiplexer. For this, first we will divide this 8 with 2. Answer will be 4. This 4 will be taken out. Now this 4 will be again divided by 2 equal to 2. This 2 will be taken out. Now this 2 will be divided by 2. Now this 1 will be taken out. Total 7. In the last circuit we saw 8:1 multiplexer will require 7 2:1 multiplexer. Now if we want to implement 16:1 multiplexer using 4:1 multiplexer, then simply we will divide 16 by 4. It will be 4. So 4. Then 4 again divided by 4 will be equal to 1 plus 1 equal to 5. So 16:1 multiplexer will be implemented using 5 4:1 multiplexer. Now if we want to implement 256 by 1 multiplexer using 16:1 multiplexer, then 256 by 16 will be equal to 16. This 16 will be here, and now this 16 will be divided by 16 equal to 1 plus 1 equal to 17. 16:1 multiplexers are required to implement a 256:1 multiplexer. Now we will implement all the logic gates using multiplexer. First we will implement NOT gate using multiplexer. Suppose this is a 2:1 multiplexer and this is input A, this is output Y. We know that this is select line, and if we give 1, this line will be connected to Y, and if we give A equal to 1, this line will be connected to Y. So we'll start our discussion. If A equal to 0, then this line will be connected to Y, Y will be equal to 1. If A equal to 1, then this line will be connected to Y, Y will be equal to 0. So this is a NOT gate confirm. Next, AND gate. Implementation of AND gate using a 2:1 multiplexer. For this we will draw a truth table. If A is 0, Y will be equal to 0. If A is 1, Y will be equal to B. So equation for Y will be equal to A bar dot 0 plus A dot B will be equal to A dot B, means this is an AND gate. Now we'll see how to select the inputs of this gate. Suppose this is AND gate, we will apply here B, here 0. When we give it a 0 here, then this AND gate will have output always equal to 0, because in AND gate if any of the input is 0, output will be 0. So this 0 will be here. Now if we'll give one input as 1, then if B is 0, output will be 0. If B is 1, output will be 1. So whichever is the value of B will be the output, so output will be B. This will B will go here. So in this way we can select the input. Now next we will implement OR gate. Now how to select inputs for this OR gate will decide. First we'll draw again an OR gate. One input is 0, another input is B. If B is 0, then 0 0 input, output will be 0. B is 1, output will be 1. Then output Y equal to B. So this B will be here. Again we'll give B, and next another input is 1. And we know that in an OR gate, if any input is 1, then output will always be equal to 1. This sorry, this B will be here, and this 1 will be here. Sorry, this B will go here, and this 1 will go here at the second input. So for this OR gate, one input will be B, another input will be 1. Now we will draw the truth table. If A is 0, output Y will be equal to B. If A is 1, output Y will be 1. So output Y will be written as A bar B plus A dot 1 will be equal to A plus A bar B will be equal to A plus B, means it is an OR gate. So a 2:1 multiplexer can be used as an OR gate. Now we will implement a NAND gate using 2:1 multiplexer. This will be input A, select line A, and we will select now output. So NAND gate. First, one input will be kept at 0. We know that in NAND gate, whenever an input is 0, output will always be 1. And if we have one input 1, other input is B. If B is 0, output is 1. If B is 1, output will be 0. So output will be B bar. This 1 will go here, while this B bar will go here. Now output can be directly written as Y equal to A bar dot 1 plus A dot B bar. So it will be A bar plus A B bar will be equal to A bar plus B bar will be equal to A dot B whole bar, reverse De Morgan's theorem. So this is a NAND gate. In this NAND gate, this input is B bar, not B. So this B bar will have to be generated. So this will be generated using a NOT gate. Sorry. This is a NOT gate. We have already seen this NOT gate will generate B bar. So for NOT gate we required 1 2:1 multiplexer. For AND gate we required 1 multiplexer. For OR gate we required 1 multiplexer, and for NAND gate we required 2 multiplexer. Now we'll see NOR gate implementation. we'll keep one input 0. Then we know that in NOR gate, uh, whenever any input is 1, output will be 0. Here, if B is 0, then output will be 1. If B is 1, output will be 0. So the output will be B bar here in this case. You can verify it from the truth table. If one input is 1, then output will be always 0. This B bar will be here and this 0 will be here. This B bar will be generated using a NOT gate. So here also we require 2:1 multiplexer. So Y will be equal to A bar B bar plus A dot 0. This will be equal to A bar dot B bar will be equal to A or B whole bar.